Introduction to Vector Theory and Physical Space. So I'm Mr. George. Today we will talk about vector theory with trigonometry, 2D area and its applications, and 3D volume and its applications. All right. So let's ask ourselves, what is a vector? So in mathematics, a vector is a quantity that has both direction and magnitude. So direction indicates the orientation or the way that the vector is pointing, so the direction. Magnitude is how long or how large the vector actually is, or just like how much the vector represents. So vectors are normally represented by an arrow. So we can see this one, this vector has a relative magnitude. It's medium size, right? And its direction is to the right. It is one informational order above something that is called a scalar. Now, a scalar is something that only conveys magnitude. So magnitude is how big or how much stuff a certain quantity has, and that's a scalar. But what a scalar doesn't have is direction. So it conveys only magnitude. So some examples of scalars are temperature, volume, and quantity. So you can only have temperature, you can only have like a amount of temperature. So it can only be 40 degrees, but it can't be pointing 40 degrees. You can't point it anywhere, right? But some examples of vectors include velocity, speed, and direction. So for example, let's say we have this car, right? And it's traveling, but we need to know where it's traveling and how fast it's traveling. So velocity is the measure of how fast it's traveling. Look, it's traveling pretty fast and it's going to the left. So that means that it has a pretty fast velocity and it has a direction. So speed is just the amount, is like how fast it's going. So we could say it's like 30 miles per hour, but velocity is 30 miles per hour to the left direction. For example, path, distance, and orientation. So if I ask you, hey, where's the nearest drugstore, right? You can tell me, oh, it's about a mile from here. Well, that doesn't tell me a lot. A mile from here is like in a circular radius. It can be in any which direction, but a path, you can tell me, oh, it's a mile from here to the north or to the northeast, right? So if you have this guy, he's going to travel along this way. It has a distance, because it is the set distance that he has to travel, and the orientation, which is the direction that he has to travel, and force. So this guy, he is pushing these boxes, right? And so he's pushing the boxes, right? And so he has a magnitude and a direction. So he's pushing it this way, he's pushing it to the right, and he's pushing it with a certain amount of force that we don't know. Why does this matter? Now, vectors can store vast arrays of information in computers through hyperspace. So for example, if we want to say, oh, a certain unit has 2, 3, and 5, just saying that we want to store like we just want to store some information, right? Then we can say, oh, we can represent it as a physical vector. So vectors also allow us to use a model for abstract dynamics, allowing us to apply physical principles. So for example, on this ball, there are two forces acting on this ball with that Jalen Brown had, right? So the force of gravity is acting upon the ball downwards, and also the force of his hand is acting on the ball to up and to the right, right? And vectors allow us to calculate and maximize efficiency and adjust to changes in information by addition or subtraction. So we have these two vectors, and we can add them to create a new vector. So what do vectors look like? So two-factor vectors are best represented by the Cartesian plane. So the Cartesian plane is just basically saying, oh, it's just this x and y axis. So here, the purple vector, so we're going to only consider this purple vector, its direction is northeast or 45 degrees, because it is 45 degrees from the x-axis. So the magnitude is calculable. So we can use our knowledge of trigonometry, since all the vectors on the Cartesian plane form a right angle that can be used to separate them into their components. So calculating the magnitude of a vector. So here we have isolated the purple vector that I was talking to you guys about. So we can see that the vector goes to the right on the x-axis a certain amount. So we can see if we look at this, where this ends and where this begins, approximately it's about 3 units. And we see that it also has a vertical component, right? So it goes up as well. This is plus 3x units, and this is plus 3y units. So it goes to the right 3, and it goes up 3, right? And so we know that according to the Pythagorean theorem, right? It's a squared plus b squared is equal to c squared, right? And so then if we replace a and b, which are the legs of the triangle, we can see that there's a little triangle right here. We can see that, oh, we can replace a with 3 and b with 3, considering that they are the lengths of the legs, equals c squared. So if we add these two together, this is 9, this is 9. 9 times 2 is 18. And so then that means that the square root of 18 is equal to c, or we can simplify it even further. Is equal to the magnitude of the vector. So the direction of the vector is northeast, and its magnitude is the square root of 18, or 3 times the square root of 2 units. All right, so let me push this down. All right, so vector addition, graphical addition. So vectors are normally represented like this. So we have these two vectors, right? So on the top number of these brackets, so we always represent them with these brackets. On the top number is its x displacement. So we can see that the red vector, it goes to the right 2, right? And so then we put 2 up here. And below it, we can see that the red vector, it goes up 5, 1, 2, 3, 4, 5, and that's how we can see that that vector down below is 5, right? And so it's this is just how we represent vectors. Like if we want to classify them, if we want to just call them things, right? This is just how we call them. We just put a little arrow on them. And we can see that we did the same thing with the blue vector, right? It goes to the right 4 and it goes up 3, right? And so if we want to add these two vectors, so for spatial addition, just stick the end of one of the vectors to the tip of the other and use the endpoint. So here we have the red vector. And what we're going to do is we're going to shift this vector up to touch so that its end touches the tip of the other. So here we shifted it up, the end, which is the tip of this one. And we could do the same thing as if we had this bottom vector, and we move this to the top of this. And we can see that both of these iterations, one starting with the other, they lead up to this point. It's the same point with each way that you want to put it, right? So it's going to be, this forms a new vector from the origin. It forms a new vector, right? So it goes from here all the way to here. And that's how we can add these two vectors, because it goes plus 6, because the addition of the displacement, right displacement, is going to be 6. And right here, it's going to be plus 8, because the addition of the vertical displacement is 8, because it's 2 plus 4 and 5 plus 3. So we can see this spatially laid out right here. And so that gives us, because it moves 6 forward and 8 up, we can create this new vector of 6 over 8. And that's how we make this new vector C. All right, so another way that we can do this is algebraic addition. So if we want to create this new vector, right, so where it's x over y, we can just set this equation up. We can set these two formats up and just numerically put them side by side. 2 over 5 plus 4 over 3. It's not really over, it's just, I'm just saying it is, right? And so then we could just add the top parts and the bottom parts, and that gives us the same answer as if we just did it visually. So these are two ways that we can add vectors. All right, so vector subtraction. So if needed, then you can translate. All right, wait, hold up. All right, wait. Vector subtraction, graphical subtraction. So if we want to subtract vectors, right? So we have these two vectors, they're the same thing. For subtraction, connect the ends of the vectors from the end of the second vector to the first equation. All right, so what does that mean? So here we have this. So the subtraction connect the ends of the vector. So we have this end right here, right? And this end right here, this end right here from the end of the second vector. So if we're considering this equation, a minus b, right? So then the second vector is going to be b, right? So then the beginning of this new vector is going to come from the top of the second vector, which is going to be b, which is going to come from here, and it's going to go all the way here. That's how you subtract vectors. The new vector created by the subtraction of these two vectors is going to be equal to the distance between the two ends, starting from the second vector. It's pretty easy. So we can see here that this one has a displacement of -2 because it starts at 4 and it ends at 2. So it has a displacement of -2, and this one has a vertical displacement of +2 because it starts at 3, ends at 5. So this creates us a new vector, -2 over 2. So algebraic subtraction, if we have these two vectors, A and B, we can just set them up like that, and then we can just subtract them using only the digits, and it's going to create -2 over 2. That's going to be the new vector if we just use our subtraction and these two original vectors. We just subtract the top ones from each other and the bottom ones from each other. All right, so here's a cool thought experiment, right? So let's say Andrew over here, he wants to move this way, and they need to move the box this way. So he's going to say, oh, well, I have to move to the back and to the left because this is his left and this is his back, right? And so he tells his friend Armando, he says, hey, we have to move to the back and to the left. But Armando, his back and his left are this way. And so they need to move the box this way, but if they both move this in their same respective directions, they're not going to go anywhere. So that means that Armando has to shift his point of reference to match that of Andrew. So are these two vectors equivalent, or are these two vectors equivalent? That's a cool thought experiment. So categorizing vectors. So vectors can be expressed in the Cartesian plane, or they can be linearized as a list or expressed equation. So here we have these two. So this vector goes back 3 because it starts at 0, it ends at -3, and this one goes up 4, right? So here in the bracket, the x change in the ends of the vector goes on top, and the y change in the ends goes on the bottom. So that's just how we do it. So one way that we can express this vector is we just say, oh, we just list these two units because it's -3x units and plus 4y units. So we just set it up as an equation. We have 4y units minus 3x units, and we have this little thing denoting that it is on the xy plane. So if we translate this over here, -3, 4 to the x over y thing, that's just how it is. But also, what is this? This little section, that's just kind of like a reminder. So thanks to the brackets at the end, vectors can be universal no matter their original orientation. So if we flip the y-plane, so let's say we have this plane, right? X and then x prime basically means negative x, or negative y, y prime, and y. So if we flip this Cartesian plane like this guy, because they are on different planes, this one has a different frame of reference, we are able to flip them. Vectors can be universal no matter their original orientation. So if you flip the plane, then x prime and y prime become the new positives. However, the new vector on this new plane, separate from this plane, is equivalent to the old one if we demarcate the reference point. So here we have this new vector, well, this kind of new frame of reference. So we have this frame of reference. So this means that this one's going to be plus 3x, and this is going to be -4yx, because on this plane, the vector goes forward 3 and it goes down 4, right? But if we demarcate that, since we have the -4y here and we have the positive 3x here, if we demarcate that here on this equation, the frame of reference is going to be x prime or xy, then that means that these two things are equivalent, because this is just flipping the frame of reference, but they are still the same thing. Because if we see here, it's this this vector is between the sectors of x prime and y, right? Then over here, when we flipped it, this vector is in the frame of reference between x prime and y. That's basically what I want to say. So applications. So a car went 3 miles east, 4 miles north, 5 miles west, 2 miles north, 2 miles east, 12 miles south, 7 miles west, 1 mile south, 3 miles west, 13 miles north. So how far is it from the starting position? you may say, oh wow, that's like a lot. That's like too much. That's too much information. Well, if we establish north, east, south, and west as y, x, y prime, and x respectively, then we could just add the sum of all these vectors. We can just add these vectors up, and then the final point of the final vector and its distance from the starting position is just going to be our answer. So here we have it went east, it went north, it went west, it went north, it went east, it went south, it went west, it went 1 mile south, it went 3 miles west, and 13 miles north. Now, what an odyssey for this car, right? So then that means that we have this final vector, right? And so then the end point of this vector and the distance between the origin here, we can create this new vector between this final point and the origin to demarcate how far it is from starting position. So f is representative of this vector, right? It's -4 and 6 because it goes in all of this. It went back 4 and up 6. So it went 4 units west and 6 units north. So if we just want to just find out the magnitude of this, so we know, okay, wait, so this is just the equation of the vectors. Hold on, let me pull myself up a little bit. So this is just the equation of the vector, right? But this doesn't tell us how far it was, right? Because this is just saying he went 4 units west and 6 units north. If we want to know exactly how far it was from the starting position, we have to use trigonometry, right? So if we have 6m, 4m, so m stands for miles here, and we want to know the distance between this, right? We want to know the purple distance. So if we utilize the Pythagorean theorem, we're just going to say that we're going to use these 2 units as the legs, because this is the hypotenuse and these 2 are the legs. So we have 4 squared plus 6 squared is equal to c squared. So we have 52 is equal to x squared. And so then the hypotenuse is going to be square root of 52x. So if we put this to the calculator, then that means that the final distance that it traveled from its starting position is going to be 7.211 miles. So in all of this, it only ever really traveled 7.211 miles from its starting point. So that's a very good application. So, oh wait, I'm not going to do that. All right. It's all right. So physics using vectors. All right. So if a rock needs 750 newtons of force rightward in order to be moved, and Antonio is pushing right at an angle 30 degrees from the ground with a force of 860 newtons, is it enough to move the rock? So Antonio here, he's pushing this rock, he's pushing really hard, and so this rock, it needs 750 newtons of force to be going this way. So then that means that the 2D vectors have x and y components. So here, the x component here that Antonio is pushing with, it has to be greater than 750, because then the rock needs 750 newtons to move rightward, right? And Antonio is pushing it at this amount. So whatever the rightward component is, it has to be bigger. So we can use this, right? So he's pushing at the rock with 860 newtons of force, and we didn't know what component of this vector, right? Because this vector is at an angle of 30 degrees. What component of this vector actually, like, well, how much is it going rightward, right? Because every single vector that's moving at an angle from the ground, it can be separated into its different components. So we have it known that it's 30 degrees from the ground. So we can use SOH CAH TOA. So SOH CAH TOA is just our little trigonometric tool. So cosine theta is equal to the length of the adjacent angle, the adjacent side to the angle over the hypotenuse of the triangle, right? So if we have it here, we know the angle of the triangle and we know the length of the hypotenuse. So we can use these 2 factors to determine the length of the adjacent side, which is this. Or the length, I say length, but it's the magnitude, because we're applying magnitude instead of length on this triangle, right? So if we have cosine 30 is equal to x newtons over 860, then it's just going to be a matter of multiplying this out over here, 860 newtons times cosine 30. And so that means that the amount of force that he is pushing rightward is going to be 744.8 newtons. But the rock needs 750 newtons of force rightward in order to be moved. So that means that because this is less than the amount needed, Antonio's force will not be enough to move the rock. All right, area and volume. So we're going to switch gears for a second. So area is the measure of a region size on a surface. It consists of two dimensions. Volume is the measure of a region size in three-dimensional space. It consists of three dimensions. So they are products of dimensions themselves. So when we say dimensions, so for example, the first dimension is just going to be a, hold on, oh, where is my thingy? It's going to be a straight line, right? Hold on. Oh my gosh. So we have this dimension, right? Okay. So we have this one dimension, right? And so then if we multiply it by another straight line, that creates a 2D area. And if we multiply by the 3D line, it creates a 3D area. Oh my gosh, I'm really bad at drawing this. Okay, how do I draw this? Okay, just pretend this is really good. Creates a 3D area. You guys see how this works? All right. I'll draw. All right. So here, you guys don't need to memorize this, but just remember that these are general equations for determining the area and the volume of certain shapes. So here we have this. If you multiply this dimension, the side dimension by this dimension is going to give you an area of a square. All right, and something that I really want you guys to see, like the only really big tidbits that I want you guys to see is that the triangle, right? So here we have a triangle, but a triangle, really what it ever is, it's a square or it's a rectangle that is cut in half. So if we see this triangle, right? If we multiply it by 2, and we have two triangles, and we overlap them like this, right? So we have this triangle, right? And if we overlap them like this, what does it create? It creates a square. You can see a square right here. Even if we have this triangle, right? If we separate it into two components, and we plaster one of these components over here, and plaster one of these components over here, as in multiplying the triangle by 2, it creates a square, at least a rectangle. What this allows us to do is that we can determine that the area of the triangle is just going to be 1/2 base times height. That's all we're going to determine. And the parallelogram is pretty much the same thing. So it's base times height, but because any which portion that you can chop off, it can be plastered over here. So we can see that if we have this parallelogram, if we cut it from the tip of this base here, it's going to be the same thing as if it were a square and you remove this part. So that's basically all we're saying. So, yeah, I don't remember why I put this here. Yeah. All right. Application. So Silvio has a beach ball with a diameter of 16 inches. So how much volume of air does the ball contain in cubic inches approximately? So the diameter of a sphere or even just a circle is going to be the distance between one end and the other in a straight line. The longest distance in a ball between one end and the other. So this is just the diameter. That's just what I mean. So the radius is just going to be half of that distance. So it's the distance from the center of the ball, of the circle, of the sphere, of the whatever, to the end of the circle or whatever round shape. What this allows us to say is that the radius is half of the diameter, or the diameter is 2 times the radius. So here we have that written out. And so here we have the equation of a sphere, right? So if we know that the radius is 8 inches because the diameter is 2 inches, right? So if the diameter is 16, if the diameter is 16 inches, right? So if we divide 16 by 2, that's going to give us 8. So that's how we know that the radius is 8. We just plug it into the equation. Boom, boom, boom. If the volume of air in cubic inches is going to be 2,144.66 inches cubed. So that's how we know what that is. So if the volume of a cup is 890.64 cubic centimeters and the height of the cup is 14 centimeters tall, what is the measure of the radius? So we can have here the equation for the volume of the cylinder, right? And so then, since we know that the volume of a cup, assuming it's a perfect cylinder, is this amount. So we can just set these amounts equal to each other. And so if we just move these things around, because pi is a constant, so we can just divide this original number by pi, and we can divide it by 14 because r squared is times 14, and because 14 represents the height of the cylinder. It's h, right? So it represents the height. And so we can just plug these things in. And if we divide this number by this, and we take the square root of it to find the radius, we find that the radius is 4.5 centimeters. So all we really did was just substitute values that we know into the equation and solve for things by doing the inverse. That's very good. All right. Application. So Christopher wants to lay tile in his kitchen. His kitchen is 3 meters wide and 9 meters long. If each tile costs $2.75 per square meter, how much will he have to spend? All right. So the area of a rectangle is length times width. And we know that a tile, the amount it costs to tile its floor is $2.75 per 1 square meter. So we have 3 meters. We know that it's 3 meters wide and, oh my gosh, I did not mean to do that. 3 meters wide and 9 meters long. So that means that the area is going to be 9 times 3, and it's going to be equal to the 27 meters squared. So that means that we can just set up a proportion. We have 27 meters squared and 1 meter squared. And since it's 1 meter squared for every $2.75, and that means we can just multiply these out. That means that the total cost that he will have to spend to tile his kitchen is going to be $74.25. All right, so let's say Tony wants to fill his pool with a hose that spews water at 0.75 cubic feet per minute. This pool is a rectangular prism with a height of 4.5 feet, a length of 6 yards, and a width of half its length, and that the pool is empty. How long will it take Tony to fill it up? This is a very good question. This is a very good question. This is a very long one, but this is not too hard. All right? Hold on. It's not too hard, believe me. All right. So knowing that it has a length of 6 yards and a width of half of its length. So if we have this 6 yards, right, and a width of half of its length, what's half of 6 yards? It's going to be 3, and it has a height of 4.5 feet because it's 4.5 feet, right? And so the width is going to be this. We're just setting variables, right? And 3 feet are in 1 yard. We have to recognize that 6 yards and 3 yards, they're not the same unit as whatever we have here, 4.5 feet. Those are not the same units. So in order to actually do this equation and do it out, we have to have the same units across the board. So the equation for rectangular prism of the volume of the rectangular prism is going to be length times width times height. So it's going to be feet. So because it's 3 feet, so it's 6 yards, right? 3 feet for every yard. So we just multiply each one of these yard units by 3. Because 6 yards times 3, 3 yards times 3 is going to be 9 and 18. Because there are 3 feet in every 1 yard. So if we multiply all of this out, it's going to be 729 feet. cubed. And this is the actual volume, but we want to know how long it will take Tony to fill it up. So if the water hose be 0.75 cubic feet per minute, then that means that we're going to have to set these things up as an equation. So here we have this, so it can cancel out. And so that means that if we multiply 729 cubic feet, if we divide it by 0.75 feet cubed for 1 minute, then that gives us a total time to fill up the pool of 972 minutes. Something that I want to go over is that we can do this multiplicative stuff. I think I already went over this, and we can convert. So, all right. Applications. More applications. Final applications. So, Paulie wants to find the volume of his ring. He drops it in a glass cup filled with water with a base of 1.5 inches. So the initial height of the water is 4 inches, and after it is dropped in, the height of the water is now 4.5 inches. What is the volume of the ring in cubic centimeters? So here we have that the height of the water changes from 4 to 4.5 inches and has a base radius of 1.5 inches. So what we're going to do is we're going to take the difference between the volumes of the initial water, and whatever difference there is between the initial and the final, and that's going to be the volume of the ring. So here we have the equation for the volume of a cylinder. It's pi r squared times height. And we have the volume initial, which is all these factors, and we have the volume final, which is going to be pi, 4.5 inches. So this is because it goes from 4 inches to 4.5 inches. So the volume of the ring plus the volume of the water initial is going to be equal to the volume of the water final. So then the volume of the ring, I already talked about. So we can set up this equation. We can plug these things in. Volume of the ring is equal to all of this. But a way that we can simplify this is using the commutative property, is that the equation is only going to be equal to the pi times 1.5 inches squared times the difference between 4.5 and 4 inches. Yeah, because a constant is going to be, because these things are equal to this. So if we have, yeah. So if we have a times b on one side and a times b on the other side, we can just factor them out, and we can just have this equation go free in the commutative property. So 1 inch. Oh, I didn't see this. So I made this. I forgot about this. So 4 inches, we have to do it in cubic centimeters. So 1 inch is equal to 2.54 centimeters. And so in order to convert from cubic to cubic, given one dimension, we have to cube the actual first dimension. So that means that 1 cubic inch is equal to 16.387 cubic centimeters, right? So because we cube 1 inch and we cube this side as well. So that means that the volume of the ring is 3.53 inches, because it's whatever this is, right? The volume of the ring is this multiplied out. But we have this measure, but we want to have it in centimeters, right? So we have to set up this and this in order to cancel them out. And so then we multiply 3.53 cubic inches by 16.387 cubic centimeters, and we have that the volume of the ring in cubic centimeters is going to be 5.57.846 cubic centimeters. So that's how we do it. So thank you for listening to this class. Feel free to reel it back if you guys have any more questions. Don't be afraid to ask questions, and thank you guys so much.